Our first one is going to be from Biplov from Wilpert. He's a computational earth scientist applying data and machine learning tools to remote sensing data at Wilpert, and he's also the co-lead of the GeoAI working group. Come on up. And Kyle. Sorry, also Kyle, who is a lead customer engineer at Wilpert as well.
No, I am a data scientist at Spatial Informatics Group. All good, all good. Do we know if this microphone is on as well? Yes, okay, do you want to pick up that one, and then we'll just pass this back and forth. Okay, and I'll give you this.
Hello. Yep. Hi, everyone. So today, So we'll talk about embeddings, of course. It's an exciting time because there's a lot of providers that are producing these embeddings. We'll talk about embeddings, both Google as well as other providers, how they differ, and a little bit of deep dive into the vector search that Val was talking about. We'll also see some of the multimodality that you can do with these embeddings, not just the image search, but also how you can incorporate some of the text embeddings. But first, just a 15-second overview of what these EU foundational model are doing. So you have a source image, and many of the pre-training using different kind of loss functions are basically trying to reconstruct this image. That gives you some form of an encoder that encodes this image into Latin space. We're calling them embeddings. And then decoder that's basically trying to reconstruct this original image. And then, as Val showed several examples, you can use them for different kind of use cases for segmentation, classification, and regression tasks. That means you also get by using just few data sets that we've already seen here. But then you could also use these embeddings to encoders to generate this vector representation that captures semantic meaning. That means if you have features that belong to same classes, that should be closer to each other and should be grouped together.
Thank you. Yeah, we'll switch on. And so we've seen a lot more interest the last few years in basically using embeddings dataset as the uniform data layer underneath software products and platforms. And so in addition to, as all of us remote sensors in the room, all the remote sensing considerations that would go into which embedding dataset to use, are you going to produce it yourself or not, we also have software considerations that are at the bottom here of how you would build something like this. And so for all of the toys that we built that we're going to show you today, we actually use BigQuery to store vector embeddings. And so how that's happening under the hood with most of the demos we're going to show is actually this vector search capability in BigQuery that does exactly the same thing that Val has already showed you with the cosine similarity index, but it's happening tabular-wise over vector embedding records in a BigQuery table.
In some of the model comparison, if you have seen from the slides before, there's something on clay as well. So in this example, I'm using clay embeddings. These are patch-based embedding, not pixel-based embedding. But the idea is that, again, with the launch of BigQuery and Earth Engine integrator, many of the functionalities that are available in BigQuery, you can now directly integrate into Earth Engine. So here on the right side, I have sort of a workflow how this works. So these embeddings, I'm using NAEP embeddings for 2021 for Washington State. And these are provided via source scope in some form of a vector format, Parquet format in this case. These are extracted and loaded into BigQuery with some transformation applied to make sure this matches the data type and all that. Then you could develop some form of a UI. In the next example, I have a UI that's developed on Earth Engine that basically lets you, click around the map, pick up your points of interest or any kind of objects that you're interested in. That gets pushed into the into the BigQuery, does the similarity search, and then gives you the results back. So again, my object of interest in this case are stadium, so like really big objects. It's really easier to see on those tiles. But I have a list of coordinates that I put in those text box there, just zooming into one of the point of interest. Then when I click search similar tiles, it basically co-locating those coordinates together, doing the SQL on the back end with BigQuery and giving you similar kind of tiles back. So you can really start to integrate some of these core functionalities available in BigQuery and use that through the Earth Engine interface too. But you could also take it a step further. So if you have read the paper, in addition to training two student-teacher model, they also train a frozen text encoder model. So that means you don't just have to rely on the points. You could literally go and start typing free flow text, NLP. So in this case, I have like a dense forest near urban areas. You can do multimodal similarity using the text NLP. And then this would then go through different encoders, text encoder as well as image encoder, does the multimodality search. On the right, sort of a workflow on how this works. So basically extract any kind of data you have, put that in BigQuery, just like before, do the transformation. You have an UI, in this case I have a UI that's developed in a Streamlight. It basically takes the user's query, does the transformation using the text encoder, and does the cosine similarity search. This one is for NYC for 2021. I just have a text box there which says ships and boats. It goes and does all the things that I've described before. And then you can just really start to get those tiles back. This gets really interesting because instead of just doing a single point of interest, for example, ships and boats, you could also say query that involves topological features like a single tree in a field that further highlight some of the use cases.
So these embeddings that Biplov has been using are patch-based, but we really want to consider also the difference between pixel and patch-based embeddings. And so what we've seen with the Google Satellite embeddings, things that Valerie has already showed, is you can get started right away with pixel-based use cases, but you can also do very little data engineering to pixel-based embeddings to create patch-based use cases like vector search. So this is just me aggregating Google Satellite embeddings against the Earth Genome Global 2024 embedding tile set. So you have, at least from a spatial domain, similar comparability, I guess. And the cool thing you see is returning way more results closer of like similar results from the Google Satellite embeddings than the Earth Genome, which makes sense with the spatial context considerations that Val has been showing. All right.